And so we're going to look at double integrals today. And basically what happens in double integrals, you know, and I'm going to kind of go along with the notes so that you see, but what we're going to do is look at applications with a volume and area of this stuff. So once again, we have, you know, we have a figure in 3 dimensions. Let's just do something simple, you know, where we've kind of got something like this. What do we call that? Paraboloid or something open upside down, things of that nature. So anyway, kind of comes down this way. So that's kind of a good 3-dimensional look there. But what we can do is say, hey, you know, let's take a particular rectangular area here. We'll call that region R in the XY plane. Okay, so region R is going to be in the XY plane. And then what we can do is kind of bring that up to the surface, right? And kind of connect. That's not very good, but anyway, this has arc to it just like the top does. Anyway, so that's kind of part of the surface, and then what we can do is say, hey, I wonder what that volume in there is, because that's kind of a rectangular thing there, right? But kind of a box shape, but it is curved on the top based on the surface that we have S. Okay, so anyway, what we're going to do, that's kind of going to be the application. So we're going to look at iterated integrals and stuff on that, and being able to take and find that volume there given a certain region. So let's talk about a little bit of the theory of that, how that works. Basically, if I've got region R, so let's look at that region R. Could be a rectangle, and then basically I've got if this is you know, I kind of drew it in here, but if I'm looking at a little portion of that would be like a tiny change in the area of this region. So we're going to call it delta sub I of A. So the ith tiny area, right? And we're going to add all these up. So if we kind of look here, once again, I've got X to the right and Y to the top like we normally do here. But anyway, this is going to be delta sub I X that way. And then this right here is going to be delta sub I Y, changing your Y's, right? And those are going to be tiny changes, right? We can take the limit as the norm of that partition goes to 0. And anyway, but R is going to be the rectangular region. We can say, hey, X1 is less than the X's is less than the X2's, or we could say less than or equal if it's okay to be equal. Doesn't really matter if it's equal or not. Y1 less than or equal to Y is less than or equal to Y2. So we have a region there. Once again, if it's a strict inequality, then the boundary line is not included. That's not going to change application stuff like area and volume that we're going to have with this. So basically, what is that delta sub I of A? So the ith change in the area is going to be given by, you know, base times height, which in this case is delta sub I X times delta sub I Y. And that's going to be the area of the ith rectangle. Okay, or subrectangle, and then we have our region R, you know, where we have a whole bunch of these, right? So, and then what we can do is let the norm of the widths go to 0 and get more and more and more rectangles and eliminate any error that we have. So then with this, basically we have a definition then that the double integral over the region R of f of xy, remember that's like your z, right? So this is like our height, but anyway, dA, so with respect to the change in the area, so this is a double integral definition, is going to be the limit as the norm of the partition goes to 0. Okay, and in this case, the size, the width of the partition is actually, we could say it's the same, right? And so they're both going to go to 0 in the same way. But anyway, this is going to be the sum. So this is like a Riemann sum. Sum I equals 1 to n of f of some particular point. So we got some point in that subinterval. We're going to call it u sub I, v sub I. So that's a particular point in the ith subinterval, and then delta sub I a. And of course, this ends up being a sum that converts to a nice double integral. So that this is kind of how it's defined, kind of how we did back in Riemann sums and those types of things in Calc 1 for certain integrals. And this is now a double integral. And of course, we have some nice theorems that overlap from Calc 1. First of all, so we do have a theorem if f of x, y is continuous on that region. So if it's continuous on R, that region given by the x's and y areas there, then f is going to be integrable on that region as well, integrable. So we can actually calculate that and get answers from that. So basically, what we're doing, we're taking, if you remember that base was a tiny rectangle, right? And then what we're going to do is we're going to keep adding, we're going to let the heights continue to go up. And so we're adding kind of tiny rectangular or square sheets of paper, depending on as we go. So these are kind of, if you think of when you buy like 500 sheets of paper in a pack, right? If you take one of those sheets out, it's paper thin, right? There's really no area to that. But when you have 500 of those sheets together, that gives an actual volume to it, all the way up to the surface on there. And of course, that surface could be curved, and things like that. But anyway, what we're doing is we're getting this volume. We're going to add up those sheets of paper with this. So anyway, so that's going to give us volume, and if we do that, then the volume for surface or under the surface, I think is how I wrote it in the notes, under the surface f of x, y. Now we're going to assume that f of x, y is greater than or equal to 0. Okay, so we're only going to stay on or above the x, y plane. So remember, this is like our z. So we're just going to be up from the x, y plane. Okay, and so volume there over the region R can be defined then as the double integral over the region R of f of x, y dA. Or more specifically, then we can say, hey, that's the double integral over region R of f of x, y with respect to x first, with respect to x first, then with respect to y. But this is also equivalent, we could switch it around. So instead of dA, we can iterate it in tiny changes in x and then with y, or we could do it the other way. So we could say, hey, that's f of x, y, double integral of f of x, y with respect to y, then with respect to x. So we're going to kind of keep this as parentheses. So we're going to do the innermost one first. So the top one, I would take the antiderivative or integral with respect to x first, then y. The second one, I would take the antiderivative with respect to y first, then x. So let's look at a specific example here. Once again, following along in your notes. I don't have my book with me, so I'm just going to follow what I have here and just kind of talk it through with you. But the double integral over region R of 3y minus 2x squared dA, and we're basically, I'm given that region region R, we're going to say, hey, this is 1 is less than or equal to x is less than or equal to 2. Sorry, it was -1. And we also have that 1 is less than or equal to y is less than or equal to 3. So we kind of have we have a rectangle with the delta x is 3 here and the delta y is 2. So that's a rectangular bottom to it. And I believe this would always be on or above the x-axis. So, well, I don't know if this is. If it is, then what we're actually calculating here could be volume. But basically, what we can do then is we can say we can calculate this one of two ways. I have where we're doing with respect to x first, and then y in the notes. And so what I'm going to do is I'm going to do it the opposite way here. So I'm going to say, hey, what's this going to be? I'm going to actually see if I can wing it here and do it with respect to y first and then with respect to x. So what I'm going to do, really, we're going to take this antiderivative with respect to y first. Now, if I'm doing it with respect to y first, what are the limits of integration? They go from 1 to 3. For the x's, or for the y's, I mean, they go from 1 to 3. Of course, from the x's, we're going from -1 to -1 to 2. So if you notice, compared to what I have, for example, 3 in the book or in the notes, it's the other way. So we're gonna do this part first, okay? And so taking the antiderivative with respect to y, first of all, I'm going to write what's not changing. I haven't done with respect to x yet, right? So what we need to do then is say, okay, well, what do we got in between? What do we got for the antiderivative with respect to y? So now y is the variable, right? Anything that's not a y is considered a constant. So we got antiderivative of 3y would be 3y squared over 2, right? And then minus, now remember 2x is considered a constant, so it'd be 2x squared y, okay? And then with respect to y, but where am I evaluating this from? I'm evaluating this from y equals 1 to y equals 3. So let's come up here then, and so I haven't taken that definite integral from x ranging from -1 to 2, but let's see what we get for the y's. When I plug in, remember when we got upper limit, we plug in, and lower limit, we plug in and subtract, right? But we only plug those in where the y's are. So when I plug in where the y's are, this would be 3 squared, which is 9, times 3 is 27 halves, minus, now I'm only plugging in for the y, right? So it's 2 times 3, which is 6, and then the x squared is there still, right? So there's nothing to plug in for the x at this point. And then minus the lower limit. The lower limit when I plug in a 1 is going to be 3 halves. And then minus, when I plug in 1 for y here, I get just 2x squared. Okay, and then, of course, whatever that ends up being, and then I'm going to take the antiderivative of that with respect to x. So really what I want to do is kind of simplify this inside of there. 27 halves minus 3 halves is 24 halves, right, which is 12. So I've got 12 minus, let's see, I'm going to add the opposite here. Add the opposite. And then I've got minus 6x squared plus 2x squared is minus 4x squared. And so that's what I have left to take the integral with respect to x. And so now x is my variable. So I go ahead and take this, whoops, I'll do this, I'm going to stay red now. So the antiderivative of this thing with respect to x, the variable is x, so that's 12x, and then minus 4x cubed over 3, right? And I'm evaluating that from -1 to 2. Okay, so I'm kind of running out of room here, but let me go up top. And so if I plug in 2 for x, once again, these are x's, right? X's upper limit, lower limit, plug those in and subtract. So plugging in 2, I've got 24 minus 2 cubed is 8 times 4 is 32. 8 times 4 is 32, right? 32 thirds. And then minus the quantity of the lower limit. If I plug in minus 1, I get minus 12. And then plug in minus 1, I get minus 1 times 4 is minus 4 thirds. So minus 4 thirds is plus 4 thirds, but I'm subtracting that whole thing. So I'm going to now add the opposite. And if I do that, I'd get 36, and then minus 32 thirds minus 4 thirds is minus 36 thirds, which is minus 12, I believe, if I did it right, which is 24. Okay, so 24 is the answer to that, and that does match if we would have done it with respect to x first and then with respect to y first, which is in your notes on page 33.5. So a couple of nice theorems that we have, you know, or just kind of remember some of the stuff that we had. We had, you know, integral of a constant with respect to x is just kx plus c, so we could do that. We could actually pull that out in front. Well, one nice thing, if we have the double integral of a constant times f of x, y, and then dA over a certain area. So here's a nice theorem. Similar deal, we can take that constant out in front because it doesn't really matter which one we do first. So it's going to be the constant times the double integral of f dA. So instead of writing f of x, y every time, I'm going to start shortening it up and just write f. But it's in two variables. It's really like a z or a height there. So we have some nice results here. We also have the double integral. If we have two integrable functions f and g with respect to that area, we can split this up. So the double integral of the sum is the sum of the double integrals. So we can do this. You know, so a lot of the stuff that we had back in Calc 1 with single integrals works also then for double integrals as well. We could also say if we have two regions, if we have, here's another one, if the region is given by region 1, union region 2, where they don't have anything in common except maybe their border, which borders are infinitesimal, right? So there's no area to a border or a line. So anyway, what we could do is we could say that the double integral over region R of f with respect to A, once again, it's either dx dy or dy dx if those are your variables for the area. What we could do is we could split this up as a double integral over the first region plus the double integral over the second region of f with respect to A. So we could certainly do that. So we have some very nice theorems, theorems plural. So we have a bunch of theorems that are very similar to what we had back in the day of Calc 1 and antiderivatives or integrals. We did use integrals for area under a curve. Now we're using double integrals. One of the applications is volume. So remember, volume, if f of x is integrable and greater than or equal, f of x, y is integrable and positive, greater than or equal to 0, so not negative, on region R. So integrable and non-negative, then we know that the volume of a solid can be given by the double integral over region R of, f of x, y, and then dA. So that's one nice application. So let's look at an example of this. I'm going to erase that so I got some room. But an example, I think this is example 4. We're looking at a volume of a solid bounded by f of xy equals 4 minus x squared over 9 minus y squared over 16, and the planes x equals 3 and y equals 2. Okay, so those are planes. I think there's a picture in the book on this, but basically what we have is that, you know, in this case, 0 is less than or equal to x is less than or equal to 3, and 0 is less than or equal to y is less than or equal to 2, and we're going to calculate that volume. So the volume is going to be, once again, I can calculate it either way, with respect to x first then y, or with respect to y first then x. So I'm going to just put double integral first, and then this is my function. Okay, and if I do it in the notes, I have with respect to x first. So instead of that, I'm going to put it with respect to y first. So if I put it for dA, if I do dy dx, then my y's range from 0 to 2. So that'd be the first one, right? And then the dx, the x's range from 0 to 3. So that's also a match where we know that ultimately whatever one is inside, we would work with that first. So in this case, I would take the integral with respect to y first, and then with respect to x. I'm not going to, because we need to get going and heading to Rhode Island, I'm not going to go through that. I assume, without looking at my book, that that is spelled out maybe the other way. I don't know if they show both ways or not. We do have another nice result. If you remember back in Calc 1, we looked at area between curves. So if I want to look at area between curves, let's just remember what we did in Calc 1. So if I have something like this, and this is f on top and g on the bottom, and we got points of intersection from x1 to x2. For these points of intersection, basically the area between the curves was going to be the definite integral from x1 to x2 of f minus g evaluated at x with respect to x. Okay, so we had that, so we could kind of get the area, because really, you know, the area under f, like if the x-axis was here, you know, the area under f was all of this, and then the area under G, I'll use green, was all of that, and then of course the difference was the area in between. So this is equivalent to definite integral x1 to x2 of f with respect to x minus definite integral x1 to x2 of g with respect to x. Right, so we had that back in Calc 1. So what do we have in Calc 2? Can we use double integrals for this? We certainly could. So area between curves, is going to be given by the double integral over region R of 1 dA. So instead of going up to f of x, if we just keep this as a 1, and of course we don't have to write the 1 in there, we can just write it as this, right? And then of course this is the double integral over region R with respect to x first, then with respect to y, or the other way, double integral with respect to y first, then with respect to x first. But notice, even though I don't have it in there, that would be like a 1 being in there. That would be area between curves. So let's look at a quick example of this. And if I have y equals 4x minus x squared and y equals x squared, and I want to look at that, basically y equals x squared. That did not write the way I meant it. Anyway, there's y equals x squared, right? The other one, y equals 4x minus x squared, looks like that. I'm looking for the area in between here, these curves. So basically what I need to do is kind of figure out, hey, what's my x and y's? So if, of course, 0, 0, 0, they're going to intersect, right? And then if I say, hey, I want the two heights equal to each other, then basically set 4x minus x squared equal to x squared, which basically 4x minus 2x squared equals 0. Factor it out, 2x times x, 2x times 2 minus x equals 0. So that says x equals 0 or x equals 2. So that equals 2 there. And anyway, of course, then along the y's, what's the y go along? You know, we can basically, the height goes from the black height right here to the blue height right here. So if I'm going to find out what the area is, if I'm going to take, let's see how I did it in my notes. I went from 0 to 2 with respect to x last. So if I want to go with respect to y first, what am I going from? I'm going from the bottom one to the top one for the height on an interval here. So I'm going to go from the bottom y value is 4x minus x squared, and the top, excuse me, no it's not, it's x squared. The bottom one is y equals x squared, it's the black one, and the top one is 4x minus x squared. So I'm taking that, and then of course of what do I have in here? Not f, but 1, right? Or I can just leave it. So anyway, if I'm doing this, I'm going to calculate this with respect to y first, and then with respect to x. So I'm going to go ahead. Didn't look like I finished that out, so I'm going to go ahead and finish this out here for that area between the curves. Once again, I'm just going to rewrite it. I had 0 to 2 for the x's and x squared to 4x minus x squared for the y's, and then dy dx. Okay, so doing this part first, basically antiderivative of 1 with respect to y is going to be y, right? Evaluated from x squared to 4x minus x squared. So upper minus lower, it's going to be 4x minus x squared, upper limit minus the lower limit of x squared is 4x minus 2x squared, right? So that's what goes in here. So then now I have the definite integral from 0 to 2 of 4x minus 2x squared with respect to x. So taking the antiderivative of those with respect to x, I'm going to get, whoops, I'm going to go ahead and do it. So the antiderivative of 4x is 4x squared over 2 minus 2x cubed over 3, and then that's going to be evaluated from 0 to 2, right? So of course the 4 and the 2 cancel, that becomes a 2, so it's 2x squared minus 2/3 x cubed evaluated from 0 to 2. So now I'm going to go ahead and plug in the 2, and so 2 squared is 4 times 2 is 8 minus 2/3 of 8 is 16/3, and then of course that's the upper limit minus the lower limit, which is 0, right? So 8 is how many thirds? That's 24/3 minus 16/3 should end up being 8/3. And of course, what's the label here? It's area between the curves, so it's square units. So anyway, that's most of what this section is. So I think I'm going to call it a day on that. I'm just going to cover one more real quick theorem. If we know that we have some minimum height for on R, we're going to look on region R. So once again, that's where you're bounding the X and Y's with some simple shape like a rectangle. But if I know that there's a minimum height, if on region R there's a height M that's less than or equal to any height on that region, which is less than or equal to some max height, capital M. If I know that, and if f is integrable on that region, then I do have a theorem that says, hey, little m times the area of that region R is going to be less than or equal to the double integral over that region R of f with respect to A, which is less than or equal to the max output for f on that region times that region A. So we do have a theorem there with upper and lower bounds, those types of things. And just to mention, if you have a bounded non-empty region R that's defined by certain easy curves like lines, so like, I mean, it could even, in this case, it's not even a rectangle, it could be a rhombus or parallelogram. Basically, the maximum value and minimum values would occur at the corner points. So that's a result from linear algebra. So some of that stuff we did on the sideboard that I haven't erased yet, along with Amber's picture. Since she's here listening, she gets to remember that I didn't erase that because she's mad at me for that. But anyway, if you have a bounded non-empty region, then the max and min values are going to occur at corner points, or basically where multiple boundary lines intersect. So that's an easy way to find what the minimum value is for f, or the maximum value is. We just plug all those in. The smallest one is the minimum, the biggest one of those is the maximum. So then we have this as well. So anyway, hopefully that's enough to get going on 13.2.